I'll be showing you in the next couple of lectures some, what I believe are some pretty cool experimental evidence from humans and animals that show how, basically, what is the first choice of the muscle to respond to changes in oxygen delivery and intracellular PO2. So if the muscle was under its own control, for example, and the muscle had a choice, what would the muscle do? Would it compromise its muscle metabolic state to maintain a given force output during an electrical stimulation? Would the muscle conform to the oxygen state and decrease its ATP requirements and force output to protect the metabolic state of the muscle? What would the muscle do? But then, once we kind of identify that circumstance and what the muscle would do under its kind of ideal circumstances, we have to consider, well, these experimental circumstances are not what's happening in healthy, normal life. When we go and exercise, if we're running a marathon, if we're expected to go to the grocery store, and for example, you know, your boyfriend or girlfriend or husband or wife are sitting outside in the 5-minute parking, you've got 6 minutes of, you know, grocery shopping to do, but you got to try to fit it in 5 minutes. How do you maintain the exercise intensity and the work intensity to get through and manipulate the area, you know, to perform that task, right? So the idea is, I'm hoping that what we'll be able to do is kind of bring everything together from the muscle metabolic and contractile function, the muscle function, and get a real understanding of exercise performance, the importance of manipulations and cardiovascular and pulmonary adjustments to support muscle metabolic function, contractile state, okay? And this then again will kind of lead into at least some of the stuff that I'll be talking about in the pulmonary physiology side, and some kind of like cardiovascular respiratory interactions, and how the burden that's imposed during high ventilations of exercise can actually result in sympathetic mediated vasoconstriction of the limb muscles, which can compromise oxygen delivery and so on and so forth. So again, the goal here is to try to start integrating a lot of the information that we've talked about in somewhat in isolation. Okay? So, models. You like models. I like models. I also need water. So, what we have here is, I'm trying to describe now the relationship between oxygen delivery and intracellular PO2. Okay, so here we have both the conservation of mass models and the mass and heat flow models operating simultaneously. All right. So here what we have is we got the muscle mitochondria. So we have an individual cell that's responsible where oxidative phosphorylation occurs. So this is the site of oxygen consumption, right? So oftentimes the oxygen transport cascade is taught from the atmosphere to the cell, and that makes sense, but in reality, courses should, including this one, but we didn't probably teach it from the cell to the atmosphere. The point is that as I showed you, remember, oxygen delivery from the atmosphere and then through the circulatory and pulmonary systems is due to this varying diffusive and convective oxygen fluxes. So pressure gradients, diffusion gradients that dictate the movement of oxygen from the air to the cell. Okay? So what we have, for example, is we've got the cell, we've got the muscle cell space, so basically we've got the cell, we've got this mitochondria basically embedded within the muscle cell, and then we have the muscle capillary. So we have, ultimately in this circumstance, we have the muscle blood flow will dictate, in large part, the capillary partial pressure of oxygen. Okay? This represents, the partial pressure of oxygen in the capillary represents the high energy component of oxygen flux from the blood into the cell. The muscle cell PO2, or the intracellular PO2, represents the low energy component of that energy gradient, or that pressure gradient, right? Concentration gradient. But then we also have a gradient between the cell and the mitochondria, where the oxygen within, say, the mitochondria would represent the low energy component of oxygen for the pressure gradient movement of oxygen from the cell space into the mitochondria itself. Okay? So let's say at the onset of exercise, well, not say, at the onset of exercise, what happens is that the mitochondria oxidative phosphorylation is activated and the rate of oxygen consumption increases. Now let's say, for example, that we went from rest to, say, 50% of your peak maximum oxygen uptake capacity. So now, the rate of oxygen consumption is fixed, okay, it's constant. Which means, remember we gave the examples about the inflow and outflow models? What happens to the inflow-outflow relationship when outflow is constant? Remember we talked about that, and then you go through the series of events. Now, when VO2 is, say, 50% of peak capacity, let's say that that is 2.5 liters a minute of oxygen consumed at the whole body level. That's constant. So that is a fixed rate of removal of oxygen from the cell. Okay? Just like it's like you have the bathtub analogy. It's a give. You don't change. You basically open up the drain, but you don't change the radius or diameter of that drain. It just removes a fixed amount. Okay? It's set. Now, oxygen uptake, say, increases to 50% of peak capacity. Let's say it's 2.5 liters a minute. Now, by removing the amount of oxygen from the cell, there creates a pressure gradient between the intracellular space and say, the mitochondria, for example. Now, this will result in a movement of oxygen from the cell into the mitochondria to try to support the increased rate of oxidative phosphorylation. As oxygen is removed from the intracellular space to support the oxidative phosphorylation and the respiratory chain in the mitochondria, what will happen to the intracellular PO2? What's going to happen to the partial pressure of oxygen within the intracellular space? It's going to go down. So remember I showed you the slide that going from rest to about 40% of maximum exercise will take your intracellular PO2 from about 40 millimeters of mercury, and it'll drop it down to about 4 to 6 millimeters of mercury, which is still above the critical PO2 to drive maximum oxidative phosphorylation. I don't know why am I yelling. Am I yelling? I feel like I'm yelling. I'm like Jack. All right. So I can tone it down a bit. So it drops to like 4 to 6, but it still remains above the critical PO2, right? So this is really what's happening in that intracellular space. The cells begin to consume oxygen, the intracellular PO2 drops, but still will remain above the critical PO2. But why? Because there has to be an adjustment that occurs to try to move oxygen from the capillary space into the cell, to try to prevent it from getting down to this critically low level, right? So now, we have now decreased the intracellular PO2, which means that we've decreased the pressure gradient or the concentration gradient for oxygen flux from the cell into the mitochondria. But simultaneously, what have we done to the pressure gradient or concentration gradient for oxygen flux from the capillary space into the cell space? We've increased it. So now oxygen begins to move along its concentration gradient from the capillary space into the cell space to try to maintain and try to help keep that intracellular PO2 above this critical level to drive oxidative phosphorylation and support the muscle cells with enough oxygen it needs. Yeah? So you begin to see how these series of events, these gradients are changing. So now what happens is oxygen moves in. So now, as this will now decrease basically the capillary PO2, and will simultaneously and dynamically begin to narrow that pressure gradient, where eventually the amount of oxygen going from the capillary into the cell would be proportional to the amount going from the cell to support oxidative phosphorylation at a constant rate of oxygen consumption. But during exercise, as Charlotte showed you, there are cardiovascular adaptations, right? Stroke volume, heart rate increase, parasympathetic withdrawal, increasing heart rate to 100 beats a minute. After about 100 beats a minute, the sympathetic nervous system activates to increase cardiac contractility, stroke volume, cardiac output. There are vasodilatory mechanisms, both metabolic and mechanical, that result in rapid vasodilation of the blood vessels, right? Shear stress-mediated vasodilation, nitric oxide release of the vascular smooth muscle. A lot of words, you should know them by now. So all of this happens. So what happens at the onset of exercise? Blood flow. So now you get this basically waxing and waning of the intracellular space, right? As the pressure gradient changes, intracellular PO2 will drop as this pressure gradient continues to drop. So to prevent intracellular PO2 from going below this critical low level to support oxidative phosphorylation at its maximal rate, you need to have an adjustment of muscle blood flow. So now muscle blood flow will increase through vasodilation, cardiac adaptations increasing in cardiac output, and increasing in muscle blood flow. Now, let's say that you have a fixed amount of oxygen content, okay? You have, say, whatever your oxygen content is, your hemoglobin, the amount of oxygen dissolved in your blood, whatever it is. Let's say that that doesn't change from the rest of exercise transition. The key to muscle blood flow is this, is that at the site of diffusion between the cell and the blood, the capillary so basically between the capillary and the cell, the blood flow, while it will increase the transit time, which means that it will move blood more quickly across these sites of diffusion, it will also result in more oxygen molecules being at the site of diffusion at any one time. So the more oxygen molecules that are at a site of diffusion, the higher the pressure gradient for diffusion of oxygen. So the way that muscle blood flow works is to try to increase the amount of oxygen molecules at a site of diffusion at any one time, which increases the pressure gradient for movement of oxygen from the blood into the cell. And so with the increase in muscle blood flow, you will have an increase in capillary PO2. So an increase in the PO2 in these microvasculature in the feed arterioles, which will serve to try to maintain intracellular PO2 levels and allow oxygen to continue to be delivered at a rate that can support maximum oxidative phosphorylation. Yeah?
I'm not sure you said the transit time would go up, but wouldn't it go down if it's faster?
Well, basically, so the transit time, so basically, I'm saying the transit time is the amount of time, the amount of time that a red blood cell would spend in a given distance of the vasculature would decrease, right? So it's moving faster. Sorry, yes. I meant the blood flow is faster, so it's moving through the system at a faster rate. But at the same time, there are more molecules of oxygen at a given site of diffusion at any one time. So thank you for Okay? So, oxygen consumes, there are these changes in pressure gradients and concentration gradients that would dictate the flux. If there wasn't a compensatory change in muscle blood flow or oxygen delivery, so really we're talking about oxygen delivery here. Oxygen delivery can be manipulated in a couple of ways. You can increase muscle blood flow, or you can change oxygen content, or you can do both, right? If you were breathing a hypoxic gas that decreased the amount of oxygen dissolved in your blood, you could compensate for that by increasing muscle blood flow to end up having the same rate of oxygen delivery. Alternatively, if you had a decrease in muscle blood flow, you could increase oxygen content and offset the two effects such that the amount of oxygen delivery is the same. So it's a combination of how much oxygen is in the blood and bound to hemoglobin versus how quickly that blood is being delivered. So it's much like the Fick equation, right? I think Charlotte must have talked about that. Oxygen delivery is really the product of the amount of oxygen in the blood multiplied by the muscle blood flow. So you can imagine that if one goes down and the other goes up, you can maintain the same rate of oxygen delivery. So then one can compensate for the other. Okay? So the idea here is that muscle blood flow is a very important way of trying to maintain the amount of oxygenation of the cell and to support oxidative phosphorylation and prevent the extent to which the other metabolic pathways, glycolytic flux, phosphocreatine degradation, and whatever stored ATP that exists needs to be broken down. But now we know that if you activate those metabolic pathways to support a given amount of ATP production or a given force production, that has negative implications on the rate of accumulation of fatigue-causing metabolites, most notably inorganic phosphate, right, which decreases myofibrocalcium sensitivity, decreases the release of calcium from the sarcoplasmic reticulum, and ultimately will impact on skeletal muscle contractile function. Okay? So, the opposite of these changes are true as well. So if you can increase muscle blood flow and increase intracellular PO2, you can have positive effects. And I'll show you some evidence of all this as we go along. So I'm going to show you the results of some old studies, and we're going to break this lecture down, or these next two lectures down, into two hypotheses, or concepts. One is called the oxygen conformer response, which is named aptly because the muscle will conform to the oxygen state of the cell, and I'll show you some pretty cool evidence of that. And then also we'll call it the net drive hypothesis of oxidative phosphorylation. Okay, so they'll begin to make sense as we move along. So what I'm going to show you is some experimental evidence describing the effects of intracellular PO2 on muscle contractile function and metabolism. Basically, the O2 former, this is what we call the oxygen conformer response, and it really, as you'll see, there's evidence that the muscle will adjust its ATP demand to the intracellular PO2. It's pretty cool of it. So, Michael Hogan, it's a gentleman that I believe he was at UCSD, University of California, San Diego, I believe these studies were done. And what they did, this is the paper published 20 years ago or so, effective gradual reduction in oxygen delivery on intracellular homeostasis and contracting skeletal muscle. So the purpose of this study, taken directly from the paper, was to test the hypothesis that when oxygen availability is reduced in a gradual manner to submaximally contracting skeletal muscle, the coupling of ATP demand to aerobic ATP supply will be tightly matched, primarily through reductions in force development, so that additional disruption of intracellular homeostasis is minimized. So, in more layman's terms, the muscle, if given a choice, will decrease its force output to prevent itself from becoming metabolically disturbed. Basically what you're saying. You don't send oxygen, the muscle will just decrease the amount of force that it's generating, decrease its ATP demands, but to make sure that it doesn't accumulate metabolites that might compromise its function. It's basically what they're hypothesizing. So, in this study, these were isolated gastroc muscles in anesthetized dogs. So this is a non-human mammal model. This is very important. They electrically stimulated the sciatic nerve, so the nerve that innervates the gastroc, to cause contractions that produce a rate of oxygen uptake, a constant rate of oxygen uptake, idea of 50 to 60% VO2P. So submaximal contractions, okay? But the key here is that you've isolated a nerve, you've stuck it to a machine, and the machine will send the impulses. So this is no longer the central nervous system that's adjusting to afferent, signals from the limbs. They've isolated basically the animal's brain from the muscle. They've used a nerve stimulator to control the muscle contraction. So this is what I mean when I say constant motor drive. Okay? Under these circumstances, the experimenters are contracting the muscle at a constant motor drive independent of the animal's own central nervous system. Okay? And then what they did, it's a cool study. They gradually reduced oxygen delivery, and as I showed you at the previous slide, you decrease oxygen delivery, you decrease intracellular PO2 through those conservation of mass and heat flow models that I described, right? They're proportional to one another. Oxygen delivery goes down, intracellular PO2 goes down. Oxygen delivery goes up, intracellular PO2 goes up. Okay? So they did it in two ways. One, they caused hypoxemia. So they gradually reduced the inspired fraction of oxygen while clamping muscle blood flow. So here what they did was they changed the amount of oxygen in the blood while keeping the amount of blood flow constant. Pretty cool. Then they manipulated the other parameter of oxygen delivery. Here they caused ischemia. So here they progressively decreased muscle blood flow while they maintained the inspired fraction of oxygen. So they manipulated the two components of basically the Fick equation, right? They changed the bulk delivery of oxygen to the muscle through muscle blood flow, or they changed the amount of oxygen in the blood by changing the inspired fraction of oxygen. And so these anesthetized, electrically stimulated dog models permit measurement at a constant motor drive, so independent of central command and independent of the animal's own central nervous system adjustments. Okay? So this is how we'll say is that this is what the muscle would do if it kind of had its own level of intelligence separated from the brain. That's not how we exercise, but nevertheless, this is what the muscle would do if it had a choice. So, these are just the experimental circumstances where to demonstrate that they were successful in manipulating the oxygen delivery. So oxygen delivery, again, is the product of muscle blood flow times by the arterial oxygen content. And so in the ischemic condition, they decreased muscle blood flow through they basically did a pump, I believe they did a pump perfusion. So basically they have like a little, like you would keep somebody during cardiac surgery, it's just like a little pump. Just pump the amount of blood into, they surgically isolate the arteries, and they just pump blood into it at a constant rate. So they can maintain muscle blood flow to these animals' isolated gastro, okay? And so they decrease muscle blood flow at a constant arterial oxygen content. And then in the hypoxemic condition, they decreased oxygen content by decreasing the inspired fraction of oxygen and therefore the arterial partial pressure of oxygen at a constant muscle blood flow. In both cases, they've compromised oxygen delivery by manipulating independently one of its two determinants. So you can see here, arterial PO2, so this is the partial pressure of oxygen in the arterial blood which is being delivered to that muscle, versus time. Here we have the control condition, the ischemic condition, and the hypoxic condition. So hypoxic condition in the open triangles, and you can see that in the hypoxic condition they gradually reduce the arterial PO2. So this is just validation of their protocol. Whereas PO2 was preserved in the ischemic condition and the control condition. In the muscle blood flow condition, you can see that they gradually restricted muscle blood flow, but not in the other two conditions. So, again, just experimental validation of the manipulations that they did. The two different ways that they manipulated oxygen delivery. Now, when I first saw this, it didn't really make sense to me. I started learning about this stuff as a postdoc, and the way that I learned about this was kind of like part of a question that I had to do for one of my 3 postdoc questions. I had to write a 30-page review article once every 3 weeks for 9 weeks, and then I had to go defend it in front of a panel of people. This stuff I actually didn't pass outright. I did the other 2, and the 3rd one I didn't, and so I had to like kind of, bolster up on my understanding of these different types of things. And not passing this question, I think, and I've said this before to many people, I think it was the most important thing in my academic career, because it forced me to learn integrative physiology a way that I had never thought before. Like, it forced me, and then it led me to teaching and all of these different things. And so now I think it was not failing, and failing, for lack of a better term, was the best thing that ever happened to me professionally, because it put me in a situation where now, like, I really believe I understand it much better. But they passed me, who knows? I don't know what would happen. But anyways, point is, when I first saw this, it's pretty remarkable to think that the muscle will do this. So you can look here, they electrically stimulate a muscle, and you can see that the rate of oxygen consumption increases in all the different conditions. Now, regardless of how they change the oxygen delivery, look at what happens relative to the control condition here. As they titrate down oxygen delivery, the rate of oxygen consumption goes down even though the muscle is being stimulated at a constant level. It's sending the same rate of nerve impulses that would correspond to this 50 to 60% of VO2. But when they decrease the oxygen delivery, you can see that the muscle itself will compromise the rate of oxygen consumption, which means that aerobic development of ATP, and therefore oxygen consumption, is decreasing. And you can see that the force output, which I think is with the reduction in VO2, the muscle will actually decrease its force output as well. Why would the muscle do this? To try to maintain its metabolic state, we think. Is there evidence for that? So, in an isolated dog muscle at a constant motor drive, as oxygen delivery is reduced, whether it's through manipulations of muscle blood flow or the amount of oxygen in the blood, both oxygen uptake and muscle force development are reduced. So, you change muscle blood flow, you change the rate at which ATP is produced aerobically. This is what's really cool, is that if you look across the different conditions, here you're looking at phosphocreatine concentrations and muscle lactate concentrations. So phosphocreatine levels kind of being an indicator of how much phosphocreatine would need to degrade if there wasn't, say, necessarily if there needed to be a shift in the metabolic source of ATP provision. And muscle lactate, of course, a signpost of kind of glycolytic flux, right? More glycolysis means greater rate of accumulation of lactate. So the amazing thing is that, to me at least, is that when you've changed the oxygen delivery state, look what happens. The lactate response and phosphocreatine responses are identical. So the muscle has conformed to the oxygen state. In the setting of a reduction in oxygen delivery and presumably therefore intracellular PO2, it decreased its force production, decreased its aerobic ATP production, decreased its rate of oxygen consumption as a means of maintaining muscle metabolic state. The muscle was like, I'm just going to decrease my force output because I don't want to perturb the metabolic milieu of my muscle, because that doesn't really make a lot of sense, right? So, in this isolated dog muscle at a constant motor drive, as oxygen delivery and intracellular PO2 are reduced, muscle metabolism was maintained. The first choice of the muscle response to a decrease in oxygen delivery is to actually decrease force production in order to maintain or protect muscle metabolic homeostasis. This is not what we do during normal exercise, but it shows what the muscle would do if it was given a choice. The trick now is starting to be in combines like, well, how does this all make sense if Jensen brings me in the lab and sticks me on a bike and asks me to exercise at 75% of my max until I can't go anymore? Because there has to be adjustments through the central nervous system, the communication of the nerves that would ultimately try to drive muscle force production, recruit more and bigger motor units, but it has a series of events, right? Accumulation of fatigue-causing metabolites, shift in the relative contribution of metabolic pathways to support a given ATP demand. So we'll get to all of that, and we'll show some experimental evidence of all that. So, basically, if we look kind of at this model again, where we have the products of oxidative phosphorylation to generate ATP, develop a given force output, and now we have motor drive, or a level of, say, muscle activation. The O2 conformer response dictates that at a constant motor drive, so here I'm showing that it just highlights at a constant motor drive, a decrease in intracellular PO2 will result actually in the muscle's first choice, which is to decrease force output and ATP demand as a means of trying to protect or prevent the other drivers that create these precursors, right, that create these substrates, which is phosphocreatine degradation, stored ATP degradation, and glycolysis, which will create or provide these other substrates to push oxidative phosphorylation. So basically, you'll just decrease the rate of aerobic ATP production to prevent the activation of the fatigue kind of causing metabolic pathways. So, now if we go to a human model, that was an isolated animal model. Go to a human model. So this is some work, these are again about 20 years ago. This is work from Australia. And they did this pretty cool study, very simple. They used gravity to their advantage here. So they used perfusion pressure. And they used where the arm is in relation to the heart to change perfusion pressure, okay? So here what they did is, here's the experimental subject. They have an arm basically plastered to a board at heart level. They raise it up 45 centimeters to above heart level to decrease perfusion pressure. So now basically the heart has to try to push blood against the pressure gradient or against gravity. And then it allows it to kind of flow with gravity and increase the pressure gradient or perfusion pressure by putting it below heart level. So they're just basically using the position of the arm in relation to heart to change perfusion pressure. And if you change perfusion pressure, you change the rate of oxygen delivery, probably by changing muscle blood flow, right? So, less muscle blood flow here, more muscle blood flow here, okay? Then what they did was they put EMG electrodes on the nerves, on the muscles of the thumbs, and so then they did an electrical stimulation of the ulnar nerve. So here we can read this: perfusion pressure in the hand was altered by raising and lowering the arm, and the effects on force production in an intrinsic hand muscle were determined. This intrinsic muscle was the adductor pollicis muscle, which is a highly fatigue-resistant muscle, was stimulated through the ulnar nerve using intermittent trains of stimuli at 25 hertz at a constant motor drive, 25 hertz, which is just pulsing, okay? Again, a constant motor drive. Again, in a stimulus protocol specifically chosen to preserve contractile function. So it wasn't a protocol of electrical stimulation that in and of itself would cause the muscle to fatigue. And the way that they did that was they didn't want the muscle to fatigue, because when they changed the arm position, they wanted to see if the muscle function would basically go from a reduced force production back to rest, or back to baseline, or an increased force production back to baseline. If the muscle was fatigued by the protocol itself, you would have a shift in the baseline activity of the muscle. So they wanted to prevent that. So the effects they described are, thus the effects we describe are of arterial pressure on working but not fatigued muscle. So again, submaximal non-fatiguing exercise. So again, experiment altering arm position alters local forearm pressure gradient for blood flow, which results in proportional changes in exercising muscle blood flow, oxygen delivery. Arm above heart level will decrease muscle blood flow, arm below heart level will increase muscle blood flow. The ulnar nerve was stimulated of the adductor pollicis, corresponding to moderate work levels, and again, this ensures that the experimental control of the muscle or motor drive is independent of the body's, of the subject's central nervous system. They've taken over control of that muscle, the experimenters. So, look what happens, much like I showed you in the isolated gastro. So here, normalized force of this adductor pollicis muscle. So you can see that the force production during stimulation is X, okay? So right now it's just saying 1, so this is kind of the control condition. And now when they move the arm to the below heart level, okay? Look what happens. Force output goes up. So the muscle is being stimulated at constant motor drive. You've manipulated arterial perfusion pressure and therefore muscle blood flow. By increasing muscle blood flow, presumably you've increased intracellular PO2. And what happens is that human hand muscle is actually able to generate more force at a constant motor drive. And then when they bring the arm back down to heart level, you can see that the muscle was not fatigued because the force goes right back to where it was prior to the manipulation of the arm position relative to the heart. If you do the opposite, now you take the arm and you raise it above heart level, decreasing muscle blood flow by decreasing arterial perfusion pressure. That thumb muscle decreases its force production pretty dramatically. You return the heart, look, it just recovers and goes back to normal. So manipulations and oxygen, so my point here is that you see how important it is to have those manipulations in muscle oxygen delivery and muscle blood flow that Charlotte was talking about, to try to maintain the state of oxygenation of the muscle and try to maintain the force output or muscle contractile function. So in the human adductor pollicis muscle at constant and submaximal motor drive, a decrease in muscle perfusion pressure and muscle blood flow decreases muscle force production, and the opposite is true in the arm above heart position, below heart position rather. Restoration of muscle perfusion and muscle blood flow resulted in restoration of muscle force production, indicating that the muscle itself was not fatigued. Yeah?
I'm wondering, like, if the muscle was fatigued, would it just go backwards to a lower baseline? Was that...
Yeah, if it was fatigued, it would generate less force at a given electrical stimulation.
Okay, so we couldn't really compare, that's why they don't want it to.
Well, the comparison is really pre-manipulation versus post-manipulation,
Okay.
and you can see that they're very comparable. So, this again, snapped from the article. What's novel here is that raising or lowering perfusion pressure strongly influences the contractile performance of the working muscle. If this effect is caused by changes in muscle blood flow, as we presume it is, then any autoregulation of flow is insufficient to offset, what does it say? To offset it. So, what it's saying is that basically the autoregulation of muscle blood flow that exists in this model was not necessarily enough to prevent that fall in force production with the change in perfusion pressure. Okay? The take-home message is that if you change perfusion pressure and muscle blood flow, increase oxygen delivery, the muscle at a constant motor drive can increase muscle force production without fatigue. And fatigue comes from those metabolites, for example, accumulation of inorganic phosphate. If you increase muscle oxygen delivery, you can generate more force for a given metabolic state of the muscle. Okay? So, again, even in human muscle, muscle force production or ATP demand conforms to oxygen delivery and therefore the intracellular PO2 at a constant motor drive. So, if we come back again, the idea is that at a constant motor drive, so again, this flash at a constant motor drive, decreasing intracellular PO2 by decreasing muscle blood flow or arterial perfusion pressure will result in a muscle's first choice to conform to that oxygen state and decrease force production and ATP demand, as a means of trying to prevent metabolic disturbances of that muscle. The alternative is that at a constant motor drive, increasing intracellular PO2 by increasing muscle blood flow, in this case by increasing perfusion pressure by putting the arm below heart level, will result in an increase in muscle force production, but without needing to change or modify the metabolic precursors, glycolytic flux, phosphocreatine degradation, stored ATP breakdown. You don't need to increase the other substrates for oxidative phosphorylation through those metabolic pathways. So the muscle metabolic state will remain relatively preserved. So let's try to summarize this then. Alterations in oxygen delivery that are caused by changes in muscle blood flow and or arterial oxygen content evoke changes in intracellular PO2. An increase in muscle blood flow should have a direct positive effect on intracellular PO2. A decrease in muscle blood flow should have a direct negative effect on intracellular PO2. The muscle, both in non-mammalian and in non-human mammals and humans, adjusts its force production and power output to conform to the oxygen state, the state of oxygen delivery, or the intracellular PO2 at a constant motor drive. So again, the central nervous system is not in a circumstance to compensate. The muscle is being stimulated external to the central nervous system or central command. Under these conditions of constant motor drive, the muscle metabolic environment or the muscle metabolic milieu remains relatively unchanged or preserved. So basically the muscle will compromise its force production to maintain its muscle metabolic state. Okay? So, the question I have for you, how are muscle force production and oxygen consumption maintained during voluntary exercise, when oxygen delivery and intracellular PO2 are altered? So now, when you're not stimulating a nerve in an animal or a human, but I bring you into the lab and I ask you to exercise on a treadmill or on a bicycle at 50% of your maximum power output, and regardless of what, keep that pace. You just keep going. You have to generate. If it's 150 watts, just keep pushing 150 watts, regardless of any manipulations that I make to muscle blood flow or arterial oxygen content. What does the muscle have to do in that voluntary state? The examples I showed you were involuntary. The examples I'm going to show you now are during voluntary. Okay? Where in the lab, I'm asking you to maintain this exercise intensity regardless of what manipulations I do experimentally. How does the body adapt? Right? So during voluntary exercise, humans have to increase muscle activation. So you got to recruit more and bigger motor units. But as you've seen now, this has implications. Some of these motor units are very glycolytic, right? They have different metabolic profiles and various other factors. And so you have to recruit more and bigger motor units to maintain a given level of muscle force production or power output when muscle oxygen delivery is compromised. I'll show you some evidence of this. However, this must occur at the expense of muscle metabolic and contractile function, right? So if the muscle's first choice is to preserve the metabolic state, but during voluntary exercise, you have to maintain the force output, something's got to give. It's going to be the metabolic state of the muscle. So my battery's dying, but this must occur at the expense of muscle metabolic and contractile function, i.e. it will occur in the setting of accumulation of fatigue-causing metabolites, as well as symptoms of muscular fatigue and discomfort. So when you start feeling pain, like muscular fatigue and increased sensations, ratings, and perceived exertion, it's because you're basically activating that muscle, right? So I'll give an example of that, but where the opposite is also true. If you could increase oxygen delivery, you would be able to basically maintain a given power output for a longer period of time before the muscle became critically metabolically disturbed. And I'll show you evidence of that. So this says basically, prove it, Jensen. Like, show us the evidence of what I'm saying is true. So now we move into this concept called the net drive hypothesis. Right? So they're interrelated, as you'll see. So as a reminder, we have the mass balance equation for oxidative phosphorylation. So we have the substrates and the products, and we know that ADP, increases in intracellular ADP, will stimulate glycolysis, will increase the rate of pyruvate production. If the rate of pyruvate production is greater than its basically utilization by the cell, and it's used by the electron transport chain, a conversion to acetyl-CoA, it results in accumulation of lactic acid, which lactic acid will dissociate immediately into a lactate ion and a hydrogen ion. Right? So we know that hydrogen ions, although their role in muscle metabolic, muscle fatigue has been questioned, we do know there is some evidence that increasing in hydrogen ion concentration in the cell can inhibit release of calcium from the sarcoplasmic reticulum and can decrease myofibril calcium sensitivity by competing with calcium binding to troponin C. This ultimately will result in accelerate the rate of fatigue development. We also know that if we have an accumulation of inorganic phosphate inhibits myosin cross-bridging and has similar effects as an increase in hydrogen ion or acidosis of the cell, which can contribute to fatigue. And again, evidence seems to suggest that it's this accumulation of inorganic phosphate that is the most important determinant of muscle fatigue development in skeletal muscle. So when we have the exact same paradigm, the substrates of oxidative phosphorylation, the ultimate product, which is ATP. We have some determinant of ATP demand, the force output that's being determined by that ATP production, and we have this concept of motor drive, or the amount that the muscle is being recruited. Okay, so we're kind of building onto this model. So, coming back to Michael Hogan again, studies done a couple of years later. So now these are studies in human subjects, again. Now what they do is they do some pretty cool stuff. This is what they call 31 PNMRS. Basically, they can label through a magnetic resonance spectroscopy device, and then they put in a tracer. They can kind of look at the refraction and breakdown of phosphocreatine and inorganic phosphate and hydrogen ion non-invasively, kind of like through a magnet in the muscle. So instead of capturing biopsies, they can kind of take magnetic pictures of the metabolic state of the muscle, so they can get more serial measures over time and see how the muscle is adapting to exercise. So in this particular case, this was a small physiological study. 6 subjects performed incremental calf plantar flexion exercise. So basically, hopefully this holds me, they're sitting on a table, they have their calf in an MRS magnet, and they're basically just doing plantar flexion exercise. Okay, so they're just doing repeated plantar flexion exercise, and they did this to exhaustion. So basically, they just did plantar flexion exercise until they couldn't do it anymore. So it's as if I brought you into the lab and I put you on a bicycle, and I asked you to exercise at this power output for as long as you can. The duration of your exercise is a determinant of your exercise performance. The longer you can perform a given power output, the better your performance, right? We talked about that, I think, in lecture 1 or 2. So again, it's all integrated, hopefully. So again, you can see, now they're manipulating different FiO2 conditions. So they had a normoxic condition, so this is the control, where the inspired fraction of oxygen was 21%, so they had a normal arterial oxygen content condition. They had a hypoxic condition where the FiO2, they decreased it down to 10%, so this would be like at pretty severe altitude, for example. This would be a reduction in the arterial oxygen content. In hyperoxia, they had 100% oxygen. So they basically created manipulations in oxygen delivery, much like they did in the isolated gastroc study, where they changed the inspired oxygen content. Normal oxygen delivery, decreased oxygen delivery, increased oxygen delivery. And what they did is they looked at changes in muscle phosphocreatine levels and inorganic phosphate using this 31P magnetic resonance spectroscopy. Okay, so again, just through this technique where they can capture or illustrate or visualize the levels of these metabolites. So Again, now this is a voluntary exercise. Person asked to contract or do plantar flexion exercise until they can't do it anymore under 3 different conditions. So here I'm showing you the FiO2, and so this is the hypoxic condition in the open circle. The FiO2 in the control in the open square, and the hyperoxic condition or high oxygen delivery in the triangle, the open triangle. So if you look, I'm showing you the percent degradation of phosphocreatine and the percent accumulation of inorganic phosphate, basically from rest. So in both cases, it starts from 100% at rest and then either goes down or goes up. Phosphocreatine will degrade, which means it'll decrease from its resting state. Inorganic phosphate will accumulate, which means that it'll increase from its resting state. So what's pretty remarkable is that if you decrease oxygen delivery through hyperoxia or increase it through hypoxia or increase it through hyperoxia, the rate of decline in the reduced oxygen delivery state of phosphocreatine is more exaggerated than in the normoxic control, and the normoxic control is more exaggerated than in the hyperoxic condition. So remember I said the slope of that dotted line between what the power output that's required and that can be performed, where those 2 points intersect represents the point at which you've reached a performance limit. So think about that graph. Visually think about that graph. That dotted line is kind of like theoretical. The expected power output is rising in the solid line, and when they intersect, that's where you stop. And time is on that x-axis. So basically what you're looking at is these are markers of that descending dotted line. And you've got time on this, time or work on this axis. And you can see that in the reduced oxygen delivery state, the muscle performs much less work than in the normal oxygen delivery state than in the high oxygen delivery state. So when there's more oxygen delivery, you can perform more work. There's a slower